All right, so this is another statics example that we're going to work through. And as I've said in some of the other examples related to this, is that I could take the structure and I can rearrange it, rotate it 90 degrees. I can take the force and put it in different directions, and the statics is still the same for this kind of structure. Now here in this particular structure, I have two force members, bars 1 and 2. And I can tell that they're two force members because there's a pin on each side. The bar that's not numbered, the one on top, that is not a two force member because there is a bar joining it somewhere in its middle. Now I'm going to make up some numbers for dimensions for this structure, just so we have something to work with, and in the load as well. So let's say that the load does go this way and it's 50 kilonewtons. Maybe I'll label this as point A and point B right here. I'm just going to make up some dimensions. Maybe this is 10 meters from there to there. 7 meters from here to here. 8 meters from there to there. And let's say 4 meters and 4 meters over this way. And I would encourage you to make up your own dimensions and practice these problems a couple different times, just so that you're not thrown off when you see something like this on an exam. It's easy to watch me do one of these problems and everything makes sense, but until you work a few problems yourself and know where you might get hung up, be real careful about these statics type problems. All right, so a typical question like this might be, tell me what the shearing stresses are at the pin A and B. Tell me what the axial normal stresses are in the two force members, bars 1 and 2. In order to do that, we need to find the reactions and the forces in the bars. If you don't know where else to start, I always recommend on statics problems to start with an overall free body diagram. And as a reminder, a free body diagram is a sketch that you draw where the structure is removed from its supports and you put the appropriate reactions in place of the supports. By that, what I mean is here's a roller. So here's a force that goes perpendicular to the surface on which the roller rests. I'll call that Bx. And then up at A, we have a pin joint. So we have two reactions. I'll call that Ax and Ay. Here's my 50 kilonewton load. And I have my two force members, bar 1 and bar 2. So let's see. Let me do the summation of moments about point A. Notice how I'm drawing in my positive direction for moments. It's always a very good idea to do that. And by this, I would have Bx times 10 plus 50 times, I guess that would be 3 meters, equal to 0. Ax and Ay have 0 length moment arms, so I'm not going to write them down in this equation. If I solve this for Bx, Bx will be equal to minus 150 divided by 10. It would be equal to 15 kilonewtons. That would be a negative 15. Summation of forces in the x direction, plus Ax plus Bx plus 50 equal to 0. This would be Ax minus 15 plus 50 equal to 0. And that would give me Ax equal to minus 35 kilonewtons. And then finally, summation of forces in the y direction. We have just Ay is equal to 0. We do not have any other forces applied in the y direction. We have a roller down at the bottom, so that's all we get. If you did have other forces applied to the structure, then Ay may not be equal to 0. You just have to work through the statics. So at this point, if you needed to find the shearing stresses at the pin, that's pretty easy to do. The shearing stress at A would be the shear force at A divided by the area in shear for the pin that's at A. And the shear force would be the square root of the sum of the squares of those reactions. If the bar was, if the pin was in single shear, we'd have pi over 4 diameter squared for the pin. If the pin was in double shear, we'd have 2 pi over 4 diameter squareds for the pin. And likewise down at B, we would have the same sort of situation where we'd have bx squared plus by squared in general divided by the area and shear for the pin. But in this case, since by is equal to 0, this works out just to be the reaction bx divided by the area and shear for pin B. And the areas may be different if the pins are different diameters between A and B. Well, if we want to find the stresses in the two force members, that's the axial normal stress would be the force divided by the cross-sectional area that I'll just note like this. And we might be given the dimensions or the area of the bar. So we need to find the forces in bar 1 and 2. In order to do this, we should draw a free body diagram of the pin. And we know this number. And the other thing that we know are that since these are two force members, the line of action of the force goes down the axis of the bar. What that means is if I denote this angle theta 2 and this angle theta 1, then that's the same angle in this equilibrium diagram. And so if we write down the equation, the summation of forces in the x direction, we'd have bx plus, let's see, it looks like the cosine component of force F2. So we'd have F2 cosine theta 2, and then we'd have the cosine component of force 1 equal to 0. Summation of forces in the y direction, we would have F1 sine theta 1 plus F2 sine theta 2 equal to 0. Now we know what Bx is, and hopefully we have enough information to find out the angles. So we need to solve for the forces. If we look at that second equation kind of carefully, we'll notice that the forces in the bars can't both be positive like I have assumed. One of them will be the negative of the other. I don't know which one is in compression without looking at it carefully, but for now, let's just solve that second equation for F1. So I'm going to write down F1 is equal to minus F2 sine theta 2 over sine theta 1. We'll put the numbers in just a minute. And then I'm going to take that F1 and I'm going to insert it into the first equation. Bx plus F2 cosine theta 2. And then I'm going to have minus F2 sine theta 2 over sine theta 1 times cosine theta 1 equal to 0. Now let's find those angles. We switch to a different color. If I look at this picture, that's 7 meters, and this is, I said that was 8 meters from here to here. So the tangent of theta 2 is equal to 7 divided by 8. Okay, so I'm going to take 7, divide that by 8, and take the inverse tangent, and that's 41.2 degrees. Likewise, I have this dimension, I have this dimension. I didn't draw this to scale, but this is 4 meters, and it's 8 meters tall. So the tangent of theta 1 is equal to 8 over 4. And that's 63.4 degrees. Okay, so now I'm going to put some numbers in. We work over here where I have a little bit more room. So Bx is minus 15. And now I have F2 cosine of theta 2, cosine of 41.2 degrees, is 0.752. And I have the sine of theta 2, divided by the sine of theta 1 times the cosine of theta 1. You should probably check my math, but I have 0.3298 F2 equal to 0. Okay, I'm going to take the 15 and move it to the other side. I'll combine those F2 terms and then divide it, and I end up with F2 being equal to 35.5 kilonewtons. All right, now F1 is equal to the negative of that value times the sine of theta 2 divided by the sine of theta 1. Now I got minus 26.2. I'm going to pause for just a second, and I'm going to check those numbers to make sure we really do have equilibrium, just to make sure I didn't make a mistake. And within rounding, those are the right numbers for those two forces. Okay, so one of them was positive and one of those was negative. The negative force for F1 means the bar F1 is in compression. When I draw a free body diagram with the arrows coming out of the pin, that's like assuming that the bar is in tension. So this would be the free body diagram of the bar 1. And I'm also assuming that the bar 2 is in tension. Now they're not both going to be in tension because of that equilibrium equation. So one of them actually points in the opposite direction. By assuming it's in tension, getting a negative number, that means it's really in compression. And so when I go to compute the stress, I can just carry that negative sign in there and note that my stress is going to be compressive. All right, so this is what I would call the forward way to work this problem, but there are other ways to set this kind of problem up. You can have an unknown force P, but you can know the stresses for the pin at A, or the stress in bar 1 and bar 2, and the safety factors. And I could ask you to calculate the largest force that could be applied to the structure. So this is just an example of the statics, but you should be able to do that in either type of situation, the forward problem or the what I would call then the reverse problem, where I'm trying to find the biggest load that can be put on the structure to maintain a certain level of safe stress.